How about now?
That's better, thanks.
Awesome. All right, so today I'm going to present to you two important considerations for using reinforcement learning effectively for decision-making in practice. And these considerations touch upon two key components of reinforcement learning. This is the estimation component, how the reinforcement learning agent estimates the models used to generalize across large state and action spaces. And the second one is a component of exploration. And the results I'm going to cover are the product of collaboration with several co-hosts, both from my time at Stanford and, of course, from here at Netflix. So let's just jump right in, since we have a lot of ground to cover. And let's start with the background we need. First, what is reinforcement learning? We all know about supervised learning. We have data and labels. What can we learn from that? And there is also unsupervised learning. We have data but no labels, and how do we make sense of it? But all this is just learning from datasets. And this is not where it stops. We may have what we call partial feedback. We take an action and we only get a reward for the action we got. We add this in and we have the multi-arm and contextual bandits. And also, our decisions may have long-term consequences. We add this in and we get reinforcement learning. And reinforcement learning is a framework about learning how to act, and there are three key components to it. Number one, generalization. How do we learn about things that we haven't seen exactly before? Number two, exploration. How do we direct our experiments towards learning things? And number three, long-term value. How do we plan for the long term? And in reinforcement learning, we have an agent who interacts repeatedly with the world and learns from these repeated interactions. So the agent observes the state of the world, takes an action A, and observes a reward which depends both on the state of the world as well as the action that the agent took. An example of a reinforcement learning problem can be seen in web services. For instance, Netflix sends messages to its members in order to help them find content that they would love watching. And depending who the member is and what it's the history of interaction between the member and the service, Netflix has the opportunity to personalize the messages it sends in order to maximize the member satisfaction. And to make successful messaging decisions, Netflix needs to learn from the data it has, experiment with data it wants to get, and also plan for the long-term member satisfaction. This is a decision-making problem in an environment with uncertainty and also delayed rewards for the member, and this is why we can say that we can cast it to a reinforcement learning problem. And in reinforcement learning, the world is generally modeled as a Markov decision process. This is a simple model of the environment and has a known state space S and action space A, and a known transition structure P, reward structure R, and initial state distribution law. And the agent interacts with the Markov decision process repeatedly over T episodes. This is what we call the sequences of interactions. And each episode has an interaction length of H, meaning that within an episode, the agent is going to collect H state action reward observations. And whereas the reward signal captures the immediate value that the agent gets when he acts, a value function specifies what is good for the agent in the long term. And the value function QSA specifies the total reward the agent should expect to get if from state S follows action A. But this value function depends on the unknown reward and transition structure of the environment. So the agent uses the trajectories it collects, these episodes, in order to estimate this value function. And why does the agent care about the value function? Because when he has this value function, he can simply take from each state the action that maximizes that value and then expect to collect the total maximum reward possible. Now, if the dimensionality of the state space is very large, it's not very practical to form a table with one value entry per state action pair. And this is where we use state action generalization, where the state action is modeled through a lower dimensional embedding, and the state action value function is parameterized by theta to generalize across the state action space using that embedding. And in order to maximize the total reward, the agent needs to balance what we call exploration with exploitation, meaning the agent needs to take actions that bring a big estimated value based on the value function the agent has estimated so far, but also he needs to take actions in order to estimate that value function in different state action pairs that are relevant for his learning more accurately. And there are several algorithms that balance this exploration-exploitation trade-off. One of these is the epsilon greedy, where the agent is going to take the argmax of the state action value function from each state with probability 1 minus epsilon, and is going to take a uniformly random action with some small probability epsilon. Another algorithm is the upper confidence bound algorithm, which says form the most optimistic statistically plausible model of the environment, and then act greedily as if that optimistic model was the ground truth. And there is a posterior sampling algorithm that says form a distribution over the model or over the value functions and sample from this distribution, and then act greedily as if that sample was a ground truth. And as we have seen so far, estimating the value function accurately lies at the heart of a reinforcement learning agent. And then it is paired with various exploration strategies. So let's focus on that estimation question. Reinforcement learning asks an inherently causal question. It says, what will happen if I take this action from my present state versus another action? And this is why the value function estimation needs to target consistent causal effect estimation rather than goodness of fit measured by mean squared error. Because if the value function targets mean squared error instead of causal effect estimation, due to the potentially weaker action signal compared to a potentially stronger state signal, there is incorrect regularization happening of the action when the action is precisely what the agent should be learning for his decision making. And this regularization can be either explicit if the agent uses L1 or L2 regularization in its model training of the value function, or it can even be implicit if the agent uses a random forest or a neural network to fit that value function, but also constrains the capacity of the model. For instance, by specifying the depth of the trees in the forest or specifying the number of the neural network layers. And another source of estimation bias is that the data collection in a reinforcement learning agent is adaptive, meaning that the agent progressively creates unbalanced training data sets because in some parts of the state space, when an action is predicted to have a highest value, is going to pull this action with higher probability than other actions. And also, this is the goal of a reinforcement learning agent, to pull actions where they are supposed to be good. This also creates the selection bias in the model estimation of the agent. And this figure is a toy example of exactly that. So say that our agent needs to learn to act in a single-dimensional state space among two actions, action 1 and 2. And in this subfigure here, we see the initial stages of learning in the agent, and the solid lines represent the true expected values of each one of the two actions and are both nonlinear. And then with the dashed lines, we have the estimates that the agent forms for the value of each action across the single-dimensional state. And at the beginning of learning, we have complete randomization. The agent doesn't still know much, so it does an exploratory phase. And when we have complete randomization, we are okay in terms of model estimation. But then if we look at later stages of learning in this next subfigure, we see what happens as the agent starts taking actions based on their estimated values, meaning adaptively. And it is going to take action 1 on the left part of the state space and action 2 on the right part of the state space, because this is where its action seems to be best. But not having enough observations of action 1 on the right and of action 2 on the left, it has to extrapolate, and this can lead to estimation bias. And now we see that these dashed lines are a bit off-centered, and as a result, there is policy errors happening in some parts of the state space where the extrapolation is the more intense. And by creating unbalanced data sets like this one is exactly what the agent is supposed to do as he learns, starts taking better actions. So how can we reconcile this progress in the agent's learning that creates unbalanced datasets with the ability to still be doing accurate estimation, which is also crucial for the continued learning and good performance of the agent? And this type of estimation bias is exacerbated when we have two real-world issues, which is the model misspecification, meaning the agent using a functional form that is not representative of the ground truth. That is common because knowing the true data generating process is often hard. And the second one is covariate shift, which we can also be expecting in practice. For instance, if we have situations where early adopters interact with the service more at the beginning, and then later this service uses the data from early adopters to define policy and use this policy for the late adopters. Okay, so these estimation challenges are present even if we do not have delayed rewards, meaning that we have T episodes with a single state action reward observation each. And then we are in what we call the traditional contextual bandit setting. And we try to estimate immediate reward of taking action A from state S instead of the long-term value. And solving these challenges in the contextual bandit setting is also essential because these learnings are going to be directly transferable to the reinforcement learning setting. And in fact, in the reinforcement learning setting, these challenges are compounded due to the long-term nature of the value signal. So the focus of this 2017 paper with Zheng-Yuan Zhu, Susan Eighth, and Guido Imbens was to address the challenges in the online contextual bandit setting. And we proposed replacing the regular model training that lies at the heart of every contextual bandit agent with important sampling-weighted training. And the agent takes action A from state S with some probability P, meaning that we have propensity scores of each action given the state of the agent. These propensity scores, when we have a stochastic agent such as epsilon greedy or Thompson sampling, can be known at every time step. If we have a deterministic agent such as upper confidence bound, then we can also estimate them based on state action data. And so once we have these propensity scores, instead of fitting regular regression for the model fitting of the agent, we fit a weighted regression where each data point is weighted by 1 over PT. So since the propensity of the observation is the probability that the agent takes one particular action from that state, intuitively, what this weighted training is doing during the online learning setting is to upweigh rare state action observations and make the action selection of the agent as good as random, even though the agent was adaptive. So this is where the term balancing comes from. And there is a very large body of prior work that has studied important sampling weighted regression for offline inference. And our focus on that particular work was to transfer these learnings in the online learning setting in a way that both improves the agent performance in practice, but also in a way where important sampling weighted training comes with optimal finite time regret bound guarantees when they are brought into the online learning setting. And why should we expect important sampling to work in an online setting? This is because it's going to help with both covariate shift and model misspecification due to the doubly robust nature of important sampling weighted regression. And what does the doubly robust term means? It means that we will get consistent estimates even if we don't have a good model of the rewards, as long as we have a good model of the policy, meaning accurate propensity scores. And an online agent may have a misspecified underlying model, and even if it is well specified at the initial stages of learning, may not have enough observations, in some parts of the state space, may not have enough observations to estimate it accurately. But because the agent always controls its policy, it always has access to accurate propensity scores to incorporate in its model estimation. And in our 2019 paper, we focused particularly on important sampling weighted training for linear contextual bandits. And linear contextual bandits assume a linear reward model with respect to the cross product of the state features and the action features. That cross product is denoted with phi. And then they learn an unknown d-dimensional parameter theta for this reward model. And in the traditional linear contextual bandits, this parameter theta can be estimated in closed form, and also its variance can be estimated in closed form using ridge regression with design matrix phi, which is the state action cross product of each one of the t observations, and the outcome vector, the vector of rewards R. And our balanced linear contextual bandits, this is how the name of these bandits are, replace the ridge regression in the model estimation with weighted ridge regression. And over here, we have the weight matrix, which is a t by t matrix. And in the diagonal of this matrix, we have the inverse propensity score of each one of the t observations. And this propensity score is also thresholded by gamma to control variance. And then, again, we can take theta hat and the variance of theta hat in closed form. But now in the estimates, as you see, we have this matrix W appearing. And after that, decision-making proceeds as before. For Thomson sampling, we are going to use a posterior based on the theta hat and the variance of theta hat. And for UCB, we're going to form an upper confidence bound using this theta hat and variance of theta hat. And we have proven that with important sampling weighted estimation, we can still match the regret bound guarantees of traditional Thomson sampling and UCB in the linear contextual setting, which is state of the art. But in practice, we should be expecting better performance for balanced linear contextual bandits when there is either model misspecification or covariate shift. When there is a well-specified model, we should generally expect a good performance for both. And here is a simple example in order to understand why we should expect better performance in practice from balanced linear contextual bandits. And in this simple example, we have two normally distributed state variables. And here are the expected reward surfaces of each one of the three actions. So the red action is action 1, the yellow one is action 2, and the blue one is action 3. And say because of the phenomenon I described earlier, this early adopters versus late adopters, we have covariate shift at the initial stages of learning, and we get the initial training observations from only a small subset of the state space. So in this small subset of the state space, which is around the local extreme of these reward surfaces, the reward surfaces are going to look mostly flat. We have zoomed in on that particular part of the state space. So this is where our initial observations come from. And first, we're going to see how the different agents behave when we have a well-specified reward model, meaning a reward model of the agent that includes both linear and quadratic terms, because this is the true data generating process. And these pictures show the evolution of action selection across the state space as we gather more and more observations. And on the left here, we see the linear Thomson sampling. And even with a covariate shift, when linear Thomson sampling has a well-specified model, because it creates a more dispersed assignment of actions, it's going to collect the bias due to covariate shift very fast. So it's going to identify that apart from the bottom left, the optimal action in the rest of the space is the red one instead of the yellow one. On the other hand, linear UCB, even with a well-specified model, because it does deterministic exploration, it assigns entire regions of the state space to the same action. And that makes the estimation a lot more difficult for UCB, and it delays the correction of bias due to covariate shift, although eventually it gets there since it has a well-specified model. And now replacing the regular regression with the balanced regression helps us find the optimal assignment much faster, as we see with the balanced linear UCB over here. And with a well-specified model, linear Thomson sampling is going to do as well as balanced linear Thomson sampling, but balancing really makes a difference in the case of UCB over here. And now we're going to see how the agents are going to behave when also we have a misspecified model of the rewards, meaning the agent only includes linear terms on its rewards when the true data generative process has both linear and quadratic terms. And we now see that covariate shift combined with model misspecification leads to estimation bias that results to incorrect decision-making for both Thompson sampling and UCB, the traditional ones, the linear contextual ones. And this happens because this bias is not corrected with the regular unweighted regression. And they both land on the yellow action when, in fact, they should be taking the red one. And by using balancing, rare actions across the state space are going to be upweighed a lot more than the frequent ones, and therefore it's going to be easier for the balanced regression with stochastic exploration to escape that bias due to covariate shift. However, with deterministic exploration, as we see with the balanced linear UCB, dealing with both covariate shift and model misspecification is quite challenging even after balancing. And we also compared the LIN-TS, LIN-UCB, balanced LIN-TS, and balanced UCB on 300 multi-class classification datasets, because this was like a toy example that we saw to build intuition. So how would these algorithms perform in a larger benchmark? And the classification dataset can be easily turned into a bandit by treating labels as actions, features as state, and by transforming the classification loss into reward. And further, we get partial feedback, which is essential when we're talking about bandits, if we only reveal the reward of the chosen action instead of all the actions, even though we have the rewards of all the actions in our fully labeled classification dataset. And in this figure, each point represents one of the 300 datasets. And with blue, we show when the balanced linear Thompson sampling agent has lower regret than the column agent on a specific dataset. And with red, we saw the opposite. And balanced linear Thompson sampling outperforms both traditional linear Thompson sampling and linear UCB, the first two, but also a policy-based contextual bandit algorithm, which is model agnostic and is called ILTCB, I love to con bandits. And also we see that, interestingly, balanced linear Thompson sampling outperforms balanced linear UCB. That's the third one over here. And these findings highlight the fact that we need both balanced regression paired with stochastic efficient exploration schemes, such as Thompson sampling, in order to have a practical online learning when we expect this model misspecification, this covariate shift issues. And this intuition is transferable to the reinforcement learning setting as well. So in this paper with Aurelian and Nathan, we continued the study of importance sampling empirical risk minimization. That's a paper recently posted. And this paper provided the first of their kind convergence rates for importance sampling weighted empirical risk minimization. For example, for regression, we provided the fast rates that leverage the strong convexity of the squared error loss. And also for policy learning, this paper provided rate optimal regret guarantees whenever exploration decays to zero. For example, when we have an epsilon greedy bandit where the epsilon decays at a rate t to the power of minus beta. And in that paper also, we did an exhaustive empirical study to see how the importance sampling weighted regression compares to unweighted regression and other weighting schemes that exist in the literature. And here, again, we compute the importance sampling weighted regression loss, the prediction loss, and we compare this error with the error that unweighted regression and other weighting schemes would have, again, in more than 50 classification datasets. And in that particular experimental setup, the data are collected by a random forest contextual bandit. And after the learning is complete, we're not on the online learning setting anymore. After the learning is complete, we want to estimate the value of each action from the data the agent collected. And in the first two rows, we used linear regression, the first one with lasso regularization, the second one with ridge regularization. And in the third row, we use a non-parametric structure, a tree with unrestricted depth. And we see that the benefits of importance sampling weighted training are the most pronounced for lasso models. Here with blue again, we depict when importance sampling weighted training has a lower error than all the other counterparts, unweighted or other weighting schemes. And the reason why we have the important sampling empirical discrimination be doing the best in the lasso case is because the model is the most restricted there. But often we use lasso models in practice because of their model selection properties, their interpretability properties. But also we see that even if we use a non-parametric model with unrestricted depth, all methods perform roughly the same. So important sampling weighted training is not going to hurt. But in practice, when we want, for instance, to have hourly retraining of our models, generally we restrict the capacity even of non-parametric architectures. We specify more shallow depth or a smaller number of neural network layers if we want to have this responsiveness of retraining the models frequently on large volumes of data for fresh recommendations. So every time we expect a capacity restriction in our models, either due to a parametric assumption or because we restrict number of layers or depth of trees, in that case, important sampling weighted regression is going to provide some benefits. So we have established the strong practical benefits of important sampling weighted regression, both for online adaptive agents and for offline learning. But we can do even better than that, and we can incorporate some other advances from the causal inference literature. And we incorporated important sampling weighted training because we wanted to correct bias due to the adaptively collected data. But by doing so, by weighing by the inverse propensity score, what we do is also introduce variance in our estimation. And W-robust is another estimator that uses important sampling weights, but instead of using the important sampling weights on the reward, it uses them on the prediction error only in order to decrease variance. But both important sampling weighting and W-robust will have large variance when the important sampling weights are large, although the W-robust's variance may be lower. And another issue is that due to the important sampling weights becoming larger and larger, each observation is going to contribute unequally to the variance of the estimator, and the central limit theorem conditions of bounded moments and variance convergence are going to be violated. And this means that neither inverse propensity weighting nor W-robust are going to be asymptotically normal. And we can see this in the plots below. Say we collected some observations with one adaptive agent, and we want to estimate the value of one action. And the ground truth is the black dashed line, and the red dashed line is our estimates. So if we don't use any important sampling in the left plot over here, we see that we have bias. The red dashed line does not overlap with the black dashed line. And if we use importance sampling either with the inverse propensity weighted estimator in the middle or with the W-robust estimator on the right, we see now that we no longer have bias, the two dashed lines overlap, but now we have higher variance, the histogram are wider, and also we have exacerbated the non-normality of the estimator. So these histograms do not nearly look as normal. And although important sampling is favorable due to these bias properties, we give up something else. And asymptotic normality is a very useful assumption to have when we rely, it's a very useful property to have when we rely, for instance, on using the estimator for post-learning inference, for using confidence intervals that rely on normality. And when during learning, we pair our estimator with exploration strategies such as UCB and Thompson sampling, which often use these normality assumptions. And to address this, in their 2016 paper, Alex Lutke and Mark van der Laan proposed to stabilize the variance of the W-robust estimator, but only in environments and policies where there is no state information, meaning non-contextual. And for the non-contextual case, Lutke and van der Laan replaced the uniform 1 over capital T weighing of each term at time t by sigma hat T inverse. So they replaced the uniform weighting of the W-robust scores at each time t by some other weights. And they call these weights adaptive because the weights of time t have to adapt to the history of observations up to t minus 1. And in order to undo the exploding variance of the important sampling weights, as the propensity scores become small, they chose to weigh observation t by 1 over square root propensity t. And the resulting estimator, called adaptive doubly robust, is unbiased and asymptotically normal. But unfortunately, this result doesn't carry over to the contextual case where many practical application lies. And the recent paper we posted with Aurelian, Nathan, Antoine Chambaz, and Mark Vanderlaan proposed the contextual adaptive doubly robust estimator for environments and policies where the reward generation and action selection is based on some context information. And this estimator is exactly the same as before, but now we see that we have state information everywhere. And what is challenging in this estimator is how to select these adaptive weights sigma hat inverse. So this term over here, the term dt, is called the doubly robust score of the observation, and it uses this important sampling weighting on the error from a reward predictor. And the sigma hat t square should be an estimate of this term's variance, of the variance of term dt. But there are several challenges into estimating this term's variance. One is that given that our data are adaptive, there are non-IID, so both sigma hat t and the reward predictor q hat t minus 1 need to be measurable up to t minus 1. The other one is that because, again, we have non-IID data, regular sample splitting strategies don't work. And the most important challenge is that we want to estimate the variance of that term, dt, under the distribution of observation t, but the agent only has a single draw from that distribution. So that is one of the most challenging parts for setting the sigma hat tau, sigma hat t weights correctly. And in order to estimate those, we can decompose the variance to the expectation of dt square minus expectation of minus square of the expectation of dt. And again, as I mentioned, like we only have only one draw from the distribution of observation OT to estimate those expectations. But we can overcome this challenge by casting the doubly robust score of each previous observation, of each observation tau before time t, as if it was drawn from the policy of the agent at time t, meaning a subsequent policy. And this is represented here by this d hat tau t. We say that the observation at time tau was collected by the agent's policy at a subsequent time t. And then we estimate the expectations by taking averages of this hat d tau t weighted by the importance sampling pt over p tau. And then after that, we can construct both this, we can estimate both these expectations and construct sigma hat t estimating the variance of term t. And if we use this particular weight, sigma hat t inverse, then the estimator, the contextual adaptive doubly robust estimator we proposed is both unbiased and asymptotically normal for the contextual problem. And in fact, this is the first unbiased and asymptotically normal estimator for data collected by a contextual adaptive learning agent. And here again, we compare the contextual adaptive doubly robust estimator with any other estimator in the literature in terms of robustness of the confidence intervals on more than 50 public classification datasets. And again, we convert a classification dataset into a contextual bandit collected by a random forest contextual bandit, and then we evaluate how often the true value of each one of 3 target policies, linear tree and non-contextual, picking always action 1, so how often this true ground truth value of different agent policies fall within the confidence interval estimated by each one of this estimator, the contextual adaptive doubly robust, and the other ones we have compared here, the direct method, inverse propensity weighting, doubly robust, MRDR. And each dot here represents a data set and it's blue when the contextual adaptive doubly robust has significantly better coverage, meaning it contains the ground truth more often. And across all our experiments, we observed that the confidence interval of contextual adaptive doubly robust has better coverage of the ground truth than any other baseline, which can be attributed to the unbiasedness and asymptotic normality of the contextual adaptive doubly robust estimator in environments with contextual information. And the last question we ask on this estimation topic of adaptive agents is, can we pair this unbiased and asymptotically normal adaptive doubly robust estimator, which is designed for the offline learning problem and has asymptotic central limit theorem guarantees, with an online learning agent that has finite time regret-bound guarantees? And the answer is yes. And in this recent paper co-authored with Jimei Ren and Zhengyuan Zhu, we proposed doubly adaptive Thompson sampling, which uses the distribution of this adaptive doubly robust estimator in place of a posterior in a Thompson sampling algorithm. This is for the multi-unbounded case, not the contextual one. So in a Thompson sampling problem, instead of Bayesian posterior updating rules, we are going to take as the posterior mean of an action A, the adaptive doubly robust estimator of the action A, and as the posterior variance, the variance of that estimator, which are shown both here. And this estimator has been constructed to be asymptotically normal. Therefore, we can use this normal as the posterior of the action. And the decision-making proceeds as before, using samples from all the actions posteriors and selecting the action with the highest sample. And in order to control how quickly these propensity scores go to zero, this is needed for the regret bound properties, we do successive arm elimination where if the dominance probability of one particular action, meaning if the probability of an action being better than at least one other action is less than 1 over capital T, meaning the total horizon, the total learning observation the agent is supposed to get, then if this is the case, then we eliminate that action. And the motivation behind using adaptive doubly robust in online learning is that the adaptive doubly robust estimator corrects the bias due to the adaptive data collection and also has the asymptotic normality properties, thus pairing well with Thompson sampling exploration scheme. And as a result, doubly adaptive Thompson sampling outperforms both traditional Thompson sampling and UCB, as well as the Thompson sampling with importance sampling that we saw earlier at the beginning of the talk. And all that while the doubly adaptive Thompson sampling algorithm matches the finite time regret bound guarantees of traditional Thompson sampling, which is state of the art. And indeed, in this simulation study, we compared the doubly adaptive Thompson sampling with traditional Thompson sampling and UCB in 20 simulated domains with number of actions ranging from 5 to 50 and 2 noise settings, a low noise setting on the left and a high noise setting on the right. And doubly adaptive Thompson sampling achieves smaller regret for both noise domains and also has smaller Bayesian stopping power, meaning that if we use a Bayesian stopping rule, doubly adaptive Thompson sampling is going to identify the best action faster than traditional Thompson sampling. And finally, here in this empirical evaluation, we compared doubly adaptive Thompson sampling with Thompson sampling UCB, the inverse propensity score weighted Thompson sampling, and the doubly robust Thompson sampling, with data from an online A/B test that we run here at Netflix. And we see that the doubly adaptive Thompson sampling, the blue one here, has both lower cumulative regret than all other baselines and also lower stopping power. And this establishes that the benefits of this algorithm can transfer over into a practical domain. Okay, so the parting thoughts on this topic is that estimation lies at the heart of any adaptive learning agent. And if we want to have reliable decision-making in practical problems based on adaptive learning agents, be it bandits or be it reinforcement learning, then we have to get estimation right. And we saw that the estimation online during adaptive learning and offline post-adaptive learning can be quite challenging. And these challenges only compound as we move from reward means to contextual reward models, meaning from multi-arm bandits to contextual bandits. And as we move from contextual reward models to value function models, meaning from bandits to reinforcement learning. And the key idea we covered is that incorporating sophisticated offline adaptive inference schemes and pairing them with efficient exploration strategies, such as Thompson sampling, significantly improves the performance of the learning agent in practice. So now we are going to turn into another pillar of practical reinforcement learning, and that is the topic of exploration. And I'm going to present to you a concept that allows multiple reinforcement learning, not a single reinforcement learning anymore, but multiple reinforcement learning agents who act concurrently to coordinate their exploration when they try to learn complex goals as a team. And we're going to see that this concept enables rapid learning of effective policies when we have multiple agents trying to achieve a common goal. And why are we looking at parallel agent learning? And in what we have seen so far, we have this episodic reinforcement learning setting, as we call it, where a single agent interacts with an environment over a sequence of finite horizon episodes. One episode ends, another one starts, and all this proceeds into a sequence. Where in fact, we have in practice millions of concurrent interactions, which may happen both asynchronously and over a long horizon, and oftentimes with very sparse rewards, which are not revealed until the very end of the trajectories. For instance, at Netflix, there are millions of concurrent and asynchronous interactions between the service and the members. And therefore, this can be thought as what we call it a concurrent reinforcement learning problem, when instead of one, we have several reinforcement learning agents, and each one is responsible for one member and interacts with that member sequentially throughout the member's membership with Netflix. And each agent aims to maximize the satisfaction of the member it serves. But there is a commonality in what the agents aim to learn, so each agent shares data and learns from the experiences of other agents. And before making a recommendation for the member it serves, the agent is going to learn from the interactions that all other agents had with the members of Netflix. And the collective goal of all reinforcement learning agents is to learn how to better serve the entire Netflix member base. And in the concurrent reinforcement learning paradigm, which was defined by a 2013 paper of David Silver et al., formally, we have all these agents interacting with multiple environment instances in parallel. Their interactions can be asynchronous and even endless. We don't have horizons of finite length. And the agents interact in parallel and share all their observations in real time and use the shared observations to update their beliefs about the unknown dynamics of the environment. And the goal of the agents is to maximize the total reward across the environment instances they are interacting with. And I will now show you three properties that the reinforcement learning has, that reinforcement learning agents should have in order to be able to coordinate their exploration in a concurrent setting. The first property is real-time adaptivity to shared observations among agents. And in this Netflix example, adaptivity would mean that each agent adapts its policy with respect to the member it serves according to the observations of all other agents so far. The second property is a property of commitment. Each agent should maintain its intent to carry out action sequences that span multiple time periods. Each agent should act in a particular way with a particular Netflix member in order to yield successful results for this Netflix member, or until it reveals new information that benefits the learning of the entire agent group. And the third property is a property of diversity. Diversity across learning opportunities pursued by different agents. And in the Netflix example, the agents should diversify the way they act with respect to each member in order to contribute useful data and learn how to better serve the Netflix member base overall. And as we will see next, these properties of efficient coordinated exploration are not very straightforward to satisfy when we move from the single agent efficient algorithms, such as the upper confidence bound or the posterior sampling algorithms, if we extrapolate the single agent counterparts of these algorithms into the concurrent setting. Because, for instance, if we extrapolate the optimistic single agent learning to concurrent RL, the counterpart would be that in each time period, the agents would form the same upper confidence bounds for the environment's dynamics based on the shared data they have. But this means that all agents are going to construct the same most optimistic MDP. Therefore, there's not going to be diversity in their action, in the way they act. From the same state, they would take the same action. Then posterior sampling is another very efficient algorithm in the single agent setting, but its transfer to the concurrent reinforcement learning setting again breaks some of these necessary properties. So with posterior sampling and concurrent RL, each agent would independently sample a new model from the shared posterior every time the agents contribute some data to the common observation buffer. But due to continuous resampling, every time an agent resamples a model, it injects extra randomness to this model, and that breaks the commitment of the agent to carry out action sequences that span multiple time periods. Finally, we can have the epsilon greedy transfer from single RL to concurrent RL, and that is simple to imagine. Again, each agent is going to update the same point estimate of the environment with respect to the data the agents share, and is going to take a random action with respect to it with some probability epsilon, and otherwise act greedily with respect to that point estimate. But again, because the point estimate is the same across agents, diversity is hindered, and also because every now and then the agents take one random action, again, that breaks their commitment to longer goals. So we proposed seed sampling, this 2018 paper with Ben Van Rooij, and seed sampling is an extension of posterior sampling to the concurrent setting, but in a way that satisfies this adaptivity, commitment, and diversity properties. And at the start of learning, each agent samples independently a random seed, and this seed is going to be specific to each agent and stays fixed throughout the course of learning. Then this seed is mapped to a Markov decision process through a deterministic function. And this deterministic function is common across the agents and reflects the agent's observations up to that time. Mapping the seed through this deterministic function gives a Markov decision process that is distributed according to the posterior, but is only unique to this agent because of the unique seed. And then each agent is going to use that MDP that is specific to him to take his next action. And if the mapping is defined in an appropriate manner, the fact that an agent maintains a consistent seed throughout the course of learning, but a seed that is only unique to him, is going to satisfy both the adaptivity, commitment, and diversity properties. And to understand a bit these different algorithms we have seen so far for the concurrent RL setting, we will now look at an animated demo. And that's an environment we have a large maze. And somewhere in the maze, there exists a big round of cheese. And this round of cheese can be in any one of these question mark locations. I know they are small, they are hard to see. And the cheese is in each one of these question mark locations with equal probability. And there is a bunch of mice navigating the maze, looking for the round of cheese, and each mouse has the map of the maze with the potential locations of the cheese, and also has a walkie-talkie to communicate in real time with all other mice. And every time a location is explored, all the other mice learn if the cheese was there or not. And the shared posterior among the mice is a uniform distribution over the remaining viable locations of the cheese. So over here, we see that with Thompson resampling, each mouse is going to resample a new question mark to pursue every time there is an update in the posterior beliefs. So we see there's a lot of back and forth. If you focus on one mouse, you will see that very often it drops what it's doing and then goes and pursues another goal because of this continuous resampling that injects extra randomness. So these mice have no commitment to pursue a goal towards the end, and that delays a lot their discovery of the cheese, although eventually they're going to get there. It's going to take some time. They found it. Okay, So here we see the concurrent optimistic approach, and the concurrent optimistic mice are really optimistic. They say the cheese cannot be very far enough from where we are, so let's all go and explore the same location. And this demonstrates that the mice do not diversify by having the same optimistic model of the environment, and that again delays the discovery of the cheese. And finally, we have seed sampling. And a seed for this problem will be that the mice start with a random permutation of the question mark locations. And then every time a question mark location is updated, they go and cross this off their list. And they also always pursue the top question mark in the list that hasn't been crossed off. So this was very fast. We saw that the mice went and found the cheese almost immediately. And this was a toy domain, but it demonstrated like why these three properties are important and how seed sampling satisfies the properties. Because the mapping from seed to MVP is updated in every time period, the agents can react intelligently to new information. Because the seeds are independent per each agent, the agents diversify their exploratory effort, and because the agents maintain a fixed seed throughout learning, this leads to a sufficient degree of commitment. So I wanted to briefly touch to how we extend this seed sampling approach from Markov decision process to reinforcement learning with generalization, because this is what we use in practice. It's usually prohibitive to use a Markov decision process in practical problems when the state action space is really large. And this is why there are a lot of advancements in literature that use reinforcement learning paired with generalization. One of the most popular ones is the epsilon greedy DQN, which is a DeepMind algorithm that had mastered the Atari 2600 game suite. And these agents train a deep neural network from all their data. And then most of the times, each agent is going to act greedily with respect to the value function from the neural network. And with some probability epsilon, the agent is going to randomize. So how can we transfer this? How can we pair DQN with seed sampling? One approach is to say that at the beginning of learning, each agent is going again to sample its own seeds. For the DQN algorithm, the seeds can be the initial parameterization of the network. So each agent samples initial parameters of its neural network. And also, each agent samples random white noise seeds, a series of white noise seeds that he's going to use in order to perturb the reward of its observation. And it's going to use both these noise seeds and the initial parameterization seed as a regularization term in order, with the same history of observations, to create a value function neural network that is specific to him. And then he's going to act greedily with respect to that Q function. But because this Q function is already randomized via the seeds, this is going to ensure exploration. And the schematic looks very similar as before. Now, instead of the deterministic function mapping, we have the value function representation here. And if we take this particular algorithm to a sparse reward problem, we can see that seed sampling can make a difference on how quickly an agent can master a problem that has very sparse rewards. And the task here was, even though it's a test domain, it is one of the most demanding test domains in terms of exploration. And we will see that, for instance, the epsilon greedy DQN that has mastered Atari cannot solve that problem quickly, particularly because it requires this deep exploration property that we talked about. And here the problem is that we have a pole that is attached to the card, and the agent can tap the card left or right or do nothing. Tapping incurs a tiny cost. And the agent will only get the reward if the pole is balanced upright and the card is centered between the walls. So this is a way to model very high reward sparsity. And reward sparsity is something that should be expected in most practical applications. And again, we see that in a complex task like this one, increasing the number of agents is not enough to learn the optimal policy fast. And here is the behavior of the DQN epsilon greedy algorithms, which although they have mastered the Atari game suite, we see that they cannot do much progress. And in fact, an exponential amount of time will be needed for these agents to solve these tasks. And actually tuning the value of epsilon, as it is common in practical applications, is not going to be enough for the DQN epsilon greedy agents we see here to solve the problem. And finally, we see how the seed sampling agents would perform in that particular case. We see that deep exploration of the environment and coordination of the data gathering among the agents is key in order to have effective team performance. We already see that the seed sampling agents, they are already starting to do something. And seed sampling does achieve this coordinated exploration through this adaptivity, commitment, and diversity properties. And as the number of agents increases, complex tasks can be learned very fast. And in our domain, this was mastered in a matter of seconds. So to conclude and wrap up the second part of the talk, concurrent reinforcement learning is very important in practice when we have millions of concurrent interactions. It plays an important role across applications from web services where services interact in parallel within the members, all the way to robot automation. And there are three essential properties for agents to perform well in that domain. These are the adaptivity, commitment, and diversity properties. And coupling seed sampling, which satisfies these properties with generalization, state action generalization, allows us to deal also with intractable state spaces while maintaining the ability to perform this deep exploration. And overall, we envision that in practice, seed sampling will enable the learning of complex wholes quickly when we have a lot of resources, a lot of parallel agents to give to a problem. So thanks for attending this talk, and feel free to reach out if you have any questions, given that we're out of time. But I think that we can take a couple of questions if people want to stay a bit longer. Nathan.
That was great. Thanks, Maria. That was super clear. That was really amazing. Obviously, I'm a fan, of course.
Thanks, Jacob.